Good morning, everyone. I'm Banuka, finally a PhD student from Monash University, Australia. Today, I'll be presenting our work, Co-Designing Extended Reality Solutions to Support Environmental Perception by People with CVI. Cerebral Visual Impairment, or CVI, is a type of visual impairment that occurs due to damage in the brain's visual processing centers rather than any physical damage to the eye. People with CVI mainly have difficulty with high-level visual processing, like recognizing faces, identifying objects, or seeing multiple things at once. There are many causes for CVI, from acquired brain injury to epilepsy. However, complications from premature birth are among the primary causes. As a result, CVI is now the leading cause of vision impairment in children in developed countries, accounting for up to 48% of severe cases in the UK and 27% in the Netherlands and 24% in the US. With these children transitioning to adulthood, CVI is said to be the leading cause of vision impairment. Research on CVI is mostly medical. Our previous review found only 3 assistive tech studies, and none of them were made for people with CVI. What that meant was we first needed a foundational understanding of the challenges faced by people with CVI. To do that, last year, we ran 3 focus group discussions with adults living with CVI. From those sessions, we identified 7 broad challenges: unawareness, locating, identifying, reading, sensory overload, mobility, luminance and contrast sensitivity. So why smart glasses? 2 reasons stood out. First, all focus group participants preferred using their sight as the main way to access information. Second, since smart glasses sit right in front of the eyes, they are ideal for supporting or enhancing how people see. With almost no research in this space, we were in a unique position to let the CVI community shape the design of AT smart glasses from the ground up. So that's exactly what we did. Developing AT smart glass solutions with CVI co-design. First, I will introduce our 2 co-designers and co-authors, Diana and Nicola. Diana had CVI since birth, but was diagnosed recently. Her perspective is of someone adapting to a diagnosis later in life. Nicola acquired CVI as a result of brain injury 20 years ago. She previously experienced typical vision. She's an expert in education and rehabilitation for CVI. We used the double diamond approach to frame our 8-month-long study with 2 CVI co-designers. This approach is method agnostic. So we started with a 2-week diary study for the discover phase. This was followed by ideation and scoping workshops to define the problem and scope out the solutions. Finally, to develop solutions, we conducted 10 development workshops. Given the limited time, I'll share some highlights from each stage. During the diary study, we explored the main challenges faced by our co-designers and also their current management strategies. This gave us a starting point for the next stage of the double diamond, where we started to define the problem. In our case, selecting the most important challenges. The ideation and scoping workshops with each of the co-designers gave us a set of 20 difficulties that define the core problem. From there, we moved on to scoping solutions to start the develop phase. We began by getting our co-designers to try the Apple Vision Pro. We chose it because our goal was to explore how high-quality visual overlays could support people with CVI. Out of all available commercial devices, the Vision Pro had the best visual fidelity. Then, in order to scope the solution space, we worked with the co-designers to select the top 4 difficulties where smart glasses could provide them meaningful support. Both co-designers chose stress due to sensory overload and locating items in cluttered environments. Diana's other 2 priorities were helping with visual attention and assist with face-to-face conversations. Nicola's other 2 were recognizing people and reading text. With the 6 difficulties identified, we moved on to iterative development. This took place across 10 development workshops. There were many interesting insights, but for now, I'll walk you through some of the key ones. Starting with locating items in a cluttered environment, we explored 28 design options. I'll start with some of the options that the co-designers did not like. First were ones that had movement. On the screen, you'll see two videos. First, a cup highlighted by a cloud of soft, moving yellow smoke drifting behind it. In the next clip, sparkling particles rise from the cup like a stream of magic dust. Our co-designers found these effects overwhelming due to unnecessary visual clutter. They also did not like ones that highlighted the general area. The first version here uses a red ring circling the cup, and the second marks it with a hovering pointer. Both co-designers found this approach as unhelpful, as they had to first interpret the cue and then look for the object. Moving on to the three options they prefer the most. First, a cup that is covered by a blue overlay. In the next, the cup is lit as if a torch were shining on it. And in the final version, only the cup's edges are outlined. Co-designers preferred these because they clearly highlighted the shape of the object without any distracting movement. So how would this solution work in practice? All of the designs were controlled using Siri with Apple Intelligence. Let me walk you through an example using this cluttered table in our lab. In this scenario, the user would say, "Hey S, find my cup." The smart glasses would then scan the environment and highlight the cup just like this. Let me explain what's happening on the screen. The video shows the glasses scanning the scene to find the cup. A pop-up reads, "Improving environment contrast," and the background dims to make the cup stand out. When the user's hand touches it, the highlight fades automatically. Next, moving on to reading text, we explored 13 design options. One of the features we explored was allowing the user to use their finger to emphasize text on the page. As you can see here, when the reader places their finger beside the line, the glasses highlight the sentence in white text with a black border, slightly enlarging it for clarity. Both co-designers liked this idea. It felt intuitive and helpful, but it wasn't their preferred option due to technical limitations that affected the stability of the highlighting. Because of this, both co-designers preferred the other option, a virtual text box attached to the top of the page that moves with the page. When the user taps on a section of the text, the content pops in a virtual text box right in front of them. A subtle feature our co-designers loved is how each sentence gently scales up when you look at it. You can see here, the first line lifts slightly above the rest. Moving on to the next difficulty, face-to-face conversations. We explored 6 design options. Both co-designers really liked adding a fixed bounding box around the person they're talking to. It helped guide their attention to the person. They also prefer darkening the environment to reduce distractions. For the difficulty of recognizing people, we explored 2 design options. Co-designers preferred a subtle name tag just under the chin. Initially, we tried putting it above the head, but it was unnatural to look above someone when they're approaching you. We also explored ways to guide visual attention and reduce sensory overload, but I'll skip those for now. So what did we learn? The outlook and optimism for smart glasses were positive. As Nicola said, initially I was skeptical about the usefulness of the glasses, but by the end, I want to buy one of these and cannot wait for it to be commercially available. But was it useful for the difficulties? For 4 of the 6 difficulties we explored, it was useful for our co-designers. For visual attention, it was a good educational tool, but struggled to be a real-time assistance tool. To reduce stress due to sensory overload, it was mostly perceived as a tool to control stress, but not a real-time assistive tool. We then identified several key considerations and challenges in making smart glasses truly effective as an assistive tool. One finding in particular stood out. Our previous work showed that people with CVI often prefer visual information only, since adding audio can cause sensory overload. But in this study, for 2 language-related tasks, reading text, and face-to-face conversations, co-designers actually preferred having both visual and auditory support. This suggests that using both channels may help in some situations, though we still need more research to see whether it reduces cognitive load. Of course, there are still important limitations to keep in mind. These were proof of concept prototypes, not polished consumer products, and they work best in controlled settings. So while the potential is exciting, real-world validation is still needed. There were many more insights and findings from this study, so we'd love to invite you to read our full paper. And finally, thank you all for your time.
Donna Garari, University of Colorado Boulder. I love this work, and I was curious if you are planning to release the code bases that you use for all these different designs.
Yes, I think I got your email before the presentation, so
I'm a student of mine.
Yeah, sorry, yes, yes. So I am actually working on updating it to the latest Vision OS 26, because a lot of the stuff we were using was with the enterprise API, which Apple now released it to the developer beta. So I have to do some modifications to bring it forward. Once I'm done, I have a few people who are waiting for that, so I will share it.
We have a question from online from Veronica. They say, as a PhD student with neurological visual impairment, I find your project very interesting. Did you incorporate any design features for minimizing adverse effects of flickering or flashing lights within the environment, or bright lights in general?
Yeah, so that is a good question, because one of the challenges was luminance and contrast sensitivity. But during our study, our co-designers did not select them as one of the challenges for them. So we did not explore any solutions, but definitely that is something we want to explore. And also there is more work needed in this space. So that's something I'll be looking into.
Okay, I think time for one more question. One more.
Hi, I'm Shawnee, and I work at Be My Eyes. And I was interested in what you see as the overlap between uses for smart glasses for folks with CVI and for folks with more maybe traditional blind or low vision needs.
Yeah, that's a good question. So one of the things we discussed in our last year assets paper was what are the key similarities and differences between people with low vision and people with CVI. One thing that's definitely that I need to highlight is CVI, because of how the vision impairment is caused by the brain, effects of neuroplasticity. Neuroplasticity has a greater effect on people with CVI, so compared to people with low vision. So during our study also, we found other papers that have explored, like for their preferred overlay color, people with CVI tend to see that more compared to other colors. And there was papers supporting that is because it is caused by a different visual pathway in the brain. So there is differences between the two groups, and there are also similarities. So yeah, I hope that answers your question.
Okay. Thanks again.
Thank you.
Right.